Yeah, that whole thing is coming. Yeah, I started.
Okay, welcome back to EE631. So Monday we don't have class, right? Monday?
Yeah.
Yeah, so we'll do them on Friday. Okay, so you should already have homework one.
Yeah.
So the due date is next Friday.
Thursday.
Thursday. Okay, so hopefully it's all going well. So we'll just continue that deadline because I won't be around, so I won't be able to extend the deadline when I'm away. Okay. All right, so let's continue on the technology. So this is supplement, right? So this is on the FinFET, and I think we kind of went over this. Basically, there are really a lot of uncertainty when the foundry are developing this FinFET nodes, basically advanced nodes, right? So there will be more and more iterations for the design, and the foundry will continuously update their model. Okay, so that's really the bottom line. All right, so I think we were gonna talk about this, but we didn't. So there's a trend where people start to do this so-called template-based analog design sales. Okay, so we know how sensitive you are right now, all the devices, right? What's the distance, to your adjacent device and all that. So people, figure that you probably won't have as much flexibility like in old days. In the old days, you can arbitrarily, not completely arbitrary, but relatively arbitrary. You can just, place those devices. You can probably rotate, right? Whatever that you think will make sense for your circuits. Now, you don't have that flexibility. They don't even allow you to randomly rotate. You cannot say, oh, I put device this and rotate 90 degrees and put another one. You don't. So now it's going towards more like what I consider more like an analog FPGA, right? FPGA, right? So FPGA, they have this all this module, right, or processing cell. It's very regular. So it looks like the analog circuit is also going towards that, right? So they would basically build all those cells, right? So we talk about this in series, right? So in order to increase the channel length, and you have NMOS, PMOS, and then even if you say, okay, I need a diode connected device, so you would just create a lot of template. Okay, and those templates, what you need to do, just that whenever you need to use this kind of device, you just copy and paste. Okay, so it's pretty much like playing the Lego. You start to do like a Lego, you just cut them, you stack them, things like that. And by the way, those are not just a randomly designed template. The idea of this template is that if you tile them up, you wouldn't violate all the DRCs. Okay, so remember I talked about this density, right? So you don't want some part to be too dense, some to be less dense. Usually when they design this, your bottom, the density will be just right. Okay, so basically you kind of have you pre-made all this template, and you know that when you pop them down, you type them up, everything will come back just right. Okay, so that seems to be what industry people are moving towards, right? So they all have this template-based design. So if one day you go to some company, you get to design some circuits in this advanced node, so you wouldn't be too surprised, if you see this kind of template-based design. Okay, Yeah, so they would incorporate, these layout guidelines, all those density concerns. They do the same thing, right? So stack the short channel to mimic the long channel device, and even the routing, right? So the routing of those wires, they would also predefine. Oh, okay, this is where you can route. Maybe this is where you can route horizontally. This is where you can route vertically. It's more and more like a digital circuits. You see that? You look at the digital. Have you guys played with digital library? Digital library, right? So link gate, NOR gate, right? So they have this VDD ground track. You don't just arbitrarily say, oh, okay, you know what? I don't like this spacing. Let me just move the VDD up, right? You never did that. What did you do? You take those logic cell. You just put them together. That's all you do, right? And by the way, that's the only reason why the tool can take over and do that, right? So yeah, so similar thing here. You kind of do more like a kind of module, even in the analog sense. Okay, and then not only you can consider the density, basically those are DRC tracks. You can also look at, remember we talked about this LDE effect, so basically layout dependent effect. You can kind of pre-consider that, right? So if you need some dummy, you can also place those dummies, right? So yeah, so this seems to be what people are moving towards at this moment. Okay, so what's in the future, right? So at a certain point, when people move to 16 or 14 nanometers, that's where the first generation of FinFET, right? And then people still go through different iterations. So 16 to 12 to 7, right? To 5 nanometers. People still were able to kind of keep squeezing what they have, through the FinFET. But realistically, we kind of run out of the margin. Okay, those process engineers, not us, not you. Okay, it's the process engineers. They pretty much run out of the limit that they can achieve, from the FinFET, right? So still there'll be some. So you can see there's some items that they still continue to try to improve, right? So for example, the short channel controls. They try to make the fins narrower, right? They still try to improve the channel mobility, right? There's a lot of variation. They also try to improve that. The contact resistance, we talk about this, right? Is very resistive, right? So they have been still trying to improve that, here and there, like a gate resistance. They try to improve the CGS and CGD. Remember we talked about the large parasitic capacitance, right? So those engineers, they continue to improve that, but it's just that at some point, you're gonna meet some limitation. Okay, so where are we now? So today, what people move to 2 nanometers and so on. This is where people are moving towards. So this is the FinFET, right? So this is like a dolphin fin, right? FinFET. So then there are two different directions. One is use nano wire. You can see that they chop off this fin into several discrete parts. Okay, that's nanowire. This is almost like a nanowire, but they don't do this fine grain, chop off, right? So they have the whole sheet, right? So that's what they call it, nano sheet. Okay, so they do the whole plate almost like that. So they do this kind of nano sheet. Sometimes you might hear people call that as a ribbon, like a ribbon-based device. That's what they meant. It's this one. At this very moment, looks like this is where the industry are moving. So they also call that as a gate all around. Why do they call it gate all around? You look at the gate, every side. You see, Before FinFET, I said that it's a 3-side, right? So now even the floor is the gate. So electron or holes, they are flowing through like a tunnel. Right now it's just like a tunnel, right? And the 4 sides, they are all electrically controlled. You control the field, you control how things are moving towards. So you can probably guess, you probably are going to get a better control, even better control, I should say, right? What's the downside? Looking at this and that. Is it easier or more difficult to manufacture this? Looks like it's more difficult. You have more steps, you have all these different layers, you need to deposit and then put the gates, and now put this. Oh my God, so those are basically their business secret, right? So unfortunately I wouldn't know how they exactly manufacture all this. You probably wouldn't know unless you join them. And in fact, from what I heard, even if you join them, you still don't know how they fabricate the whole thing, because they will chop off so small, tiny. Okay, you just work on this. You work on that. How do you put the pieces together? You have no idea. So
for like the stack nanosheet shown, are they usually use it as like a one big gate, or like each transistor is connected to different?
Oh no, so all these are shorted together, right? So this is one transistor.
Okay.
Yeah. If you want to do that, okay, separate this. So this is one transistor and another transistors. I don't know how that works, but just visually, just visually checking is probably a lot more difficult. I mean, do you guys agree? If I need to cut this gate, right? Because I think she's right? So if, technically speaking, I can divide this into, let's say, 4 different devices. 4 different gates. By the way, so that's one issue. Another issue is that, how do we get the drain and source out? That's also another issue, right? Because even if you said there are 4 different transistors, right? So that you need to get 4 drain terminal and 4 source terminal. You need to tap them out separately. So I think, from my naive perspective, I think it's probably very hard. I think it might be just better, just say, all these stacks are basically one transistor. But that, trust me, that's already very difficult. It's so difficult to get high yield, to get those transistors perform, right? So that's don't forget, right? So their goal is not just to get the 80% of the transistors to work. They need to make sure all the transistors to work. So just think about what's the difficulty, those foundry are working on this. Okay. By the way, shown on the right, those are the real devices. So they really take I think they looks like the X-ray image. So actually they take the cross sections, and this is really how that looks, right? So actually it looks pretty good. Yeah. It looks very uniform and all those devices. Does that remind you of hot dog or donut sandwich? It's just all the kind of funny shape, right? Donuts. Okay. So I think this is what the layout may look like, right? Don't forget the layout is always the 2D, right? Doesn't matter if you're doing the FinFET or nano sheet, right? But then if you cut it out, this is a cross section. You're gonna see all this channel will be like that, right? Okay, so just give you some vertical view. There are also people trying to use a 2D material, 1D material, so they really try to change instead of using silicon, the crystal, structures, now they go to the 2D, even 1D carbon nanotube. So this is still pretty much ongoing. So there are a lot of R&D efforts. I know there's some device people here, so you probably can testify, right? So those are the people are pushing, but I think it's still a little bit far away. So you're probably not gonna see this next year or in 2 years. You're talking about probably another 10 years or so, before you can really become a mainstream. Again, what comes down to is still the yield, nothing else. People have demonstrated 2D, 1D phenomenal performance, single device, right? So that's what the research group, right? So if you are in the device, if you're a PhD student, your device group here, you probably work on one of those projects, right? To show that, you go to clean room, you say, oh my God, this is world record performance. They cut the subthreshold leakage current to be like nothing. The problem is that can you build this in billions and billions of transistors, and still every transistor is close to nothing leakage current. Right? So that's is the difficulty. Okay. Yeah, so I think that's the same thing. Yeah, so they will have the different flavors for those transistors. Okay, so so conclusion, right? So the Moore's law, extended, one way or the other, right? So they change different structures, it's even though it's not like old days, they just keep shrinking the geometry. In the old days, that's pretty much what they do, and they change the doping, they change those chemical processes. So it's still way in life. It's not even sick, right? So that's what the world is moving towards. So yeah, so the right now the whole area scaling, everything is really by the device innovation, right? So you look at the nano sheet, you look at the FinFET, right? So it's not so much by just shrinking the W and L. That's what we are facing today. The stability, I talked about it, right? So unfortunately, all the scaling concerns are for digital circuits, right? It's not so much for the analog. Okay. So yeah, so the design, we need to kind of react on our end, given all these, device, limitations. I think that's the bottom line. So you really need to understand, what aspect you can really get in this new technology node, right? So as long as you kind of calibrate yourself and you understand, in this technology node, this is what I can benefit, this is what I cannot benefit, then I would say that you are in good shape, right? Then you start to decide what circuit technique that you should do. Okay, so obviously there are a lot of references. So if you get bored, let's say this long weekend, you can read one by one. So there are 50 reference papers. So yeah, so all those are basically the relevant papers that kind of walk you through different aspects of this, list. Okay, any question? I will not test this, in any of the exam or homework. Okay, this is a little bit more like device, but I think we are at the point where we get a lot more impact because of the device fabrication, right? Just because you look at all this physical location, orientation, right? It's start to affect our circuit. So that's why we spend a little bit more time to understand what's going on there. Only for that reason. In the old days, you see, I don't even talk about this because the square law device is good enough. Why do I bother to tell you or to teach you? I mean, you can take the device class, right? You just assume, they do something, they just give me something called VTH, right? Everything just fit nicely with this square law, right? So that days has passed, unfortunately. So this is a new world that we're facing. Okay. So if no more question, let's finally let's start on EDC. Okay. But before I talk about any circuits, we unfortunately need to understand still on the very high level. Okay. So we will be mostly focused on quantization, and we need to start to understand different terminologies, related to ADC, and understand what's the typical specs. Okay. So the goal is that after these lectures, you should be able to go and download any data sheet related to ADC. You should be able to start to understand. Oh, I think that's what that means. Okay. Oh, that's why they sell more expensive for this ADC, right? So that's kind of the goal. In this field, there are a lot of useful tutorial, I would say, right? So industry, they call it application notes. Okay, all these are online. Google search, you will find them. Okay, so there are a couple good ones. I think I will also upload this to the website. But you can find it yourself also, right? So there are a lot of good tutorial to teach you, right, how to understand the different spec of the ADC and roughly at the high level how that works. For what reason? Usually you don't see people so nice, right? Just post all this, teach you how everything works. My take is that they post all this because they want you to buy their ADC. Right? So that's why they want to teach you very well. They want to teach you, once you buy our ADC, this is how you should make it function and then work well. But because of that, this actually do us some benefits because we are learning, right? We are learning this new topic and that become our fantastic learning material. Okay, so let's start from the very basic, analog to digital conversion, has two parts of the quantization. The first part is called quantization in time. So we talk about this. What is quantization in time? Remember all the sampling stuff, right? We sample at a particular time point. That's that. Okay. So even though in math, we pretty much model that as multiplied by a delta function, right? Delta trend. But in reality, there are a lot of details. There are aperture uncertainties, there are sampling clock jitters, and so on and so forth. After I finish this ADC basics, I will come back to that point. Okay, I will show you all the defects related to sampling action. Okay, so hopefully at that time you're gonna start to appreciate more why sampling is not as simple as just view that as multiplied by a delta function. Okay. The second part, which I have been postponing, right? So remember in the signal processing lecture, I said that now you just assume there's infinite bits resolution. I postponed this so-called amplitude quantization. Okay, but from now on, we're gonna start to touch on this. Okay, so we know that to truly get to the digital signals, right? The digital code has certain bits. Because certain bits, so you have a finite discrete voltage level, right? Or amplitude level. So that's what we're doing here. Okay, so it's not continuous. The amplitude is not continuous. We got to make it discrete, right? So we also need to basically slice, right, this continuous amplitude into discrete steps. So that's what we're doing. Unfortunately, because the slicing, so it depends on how well you slice. Okay, so let's say if I don't slice in a very fine grid, versus I can slice that in a very, very, very fine steps, which one is better? The finer step has to be better, right? You just think about it, right? Because you can represent the original signal better. Yeah, so your intuition is absolutely correct. And I'm actually done. This ADC is just as simple as that. Whoever can slice, or basically quantization, right, in amplitude and also in time, in a very accurate fashion, you win. you win the big time. Okay, you can sell your product much more expensive. Your overall system is gonna perform better in most cases, right? So yeah, so that's basically what we're gonna go into, right? So we're gonna analyze, what's the impact of those quantizations, and some of those quantizations can be non-uniform. So what is the impact? All right, so let's start from the very basic. So this is gonna be very important. So we're gonna start to slice the amplitude. How do we slice? So basically, if this is my input, right? So we want to slice the amplitude, right, in a certain grid. All right. So the transfer function of this slicing is shown on the bottom left here. You have a V in. If you are analog signal, your amplitude is continuous, right? So your V in can be anything. And your output, if I slice it, unfortunately, you see, you're gonna have this step function, the staircase. Why? Because that means that, you see, if your input is within this step, this region, the code I can represent you is only this particular code, nothing else, right? Because I only have a finite steps that I can represent you, right? So it's all about this step case, right? Staircase, right? All right. So and to represent all this staircase, you need the digital bits, right? Digital bits. So let's say this is the smallest level. Usually you use the smallest digital code, right? So let's say if I do a 3-bit, what's the smallest code? 0, 0, 0. What's the next code that I can represent? 0, 0, 1. Okay, that's exactly what the ADC is trying to do. Okay, so basically every code represents one of these levels. So this is the symbolic representation, right? You have an analog V in, you do ADC, you have a certain number of bits. So here you have an n, actually n plus 1 bit, right? Right there. So it's quantized. But then, I know this quantization won't be perfect, right? Because if I want a perfect, I need this red line. The red line is V in equal to V out, right? But now it's not, because I do finite quantization. So if I put back to the DAC, so remember the DAC is to nothing but convert the digital code back to some analog quantity, right? So basically it gives you this staircase, right? So this output is this black staircase, and the red is the ideal perfect V in value. So V out should equal to V in. All right, so we need to define the error, and the definition is super simple. You look at the perfect line, which is red line, and you look at the actual black staircase. You look at the difference, and that's your error. All right, so what's the error? You look at this, if I look at the delta, do you agree that sometimes the error is positive, sometimes the error is negative? And in fact, some error are 0. Do you see the points where there's no errors? Whenever this red line intersect with the black staircase, 0 errors, right? 0. So if you plot it, this is the error function, right? You see this V errors over the range of V in. You see sometimes it will be positive, sometimes it will be negative, sometimes it will be 0. Okay, what's my maximum error and what's my minimum error? So exactly, so it's exactly on the step size, right? So if the step size here is delta, you see you are always bounded by delta over 2 to negative delta over 2.
But if you notice that, can't you, like once it's digital, can't you do like some kind of compensation, like
compensation. What kind of compensation?
Because you know the V error corresponding to V ins.
Ah, okay, I see. So you are suggesting that, hey, if I know the error, I can subtract it out,
Something like that.
right? You can subtract out, right? That's actually a very interesting thought, right? So if I know that, okay, my error here is, so let's say V in minus V out right here, right? So let's say we are negative 2 millivolts. Then all I need to do in the digital domain, I just add that 2 millivolt back. Does that work?
No, it's not
If
one.
you know your signal is going to be just straight line, then okay.
You see that? Yeah. So the idea actually is very tempting. Actually, the first time I look at this, I thought about similar things. Yeah, I said, okay, well, what are you guys doing? You know the errors, then you can just add back, right, or subtract. The problem is that there's a chicken egg issue here. You don't even know what's your V in. How do I know what's your V in? Without the ADC, let me tell you, without the ADC, do you know what is your V in? You don't even know. Right? Because in order to know the error, you actually know where you are, right? So you don't know the V in, that's why we need the ADC, right? So this is what I said, there's a chicken egg issue here, right? If somebody else is gonna tell you what's the V in value, okay, forget about it, you don't need to design this ADC. And people already tell you, right, what's the V in, and why do you need ADC, right? Okay. All right, but that's a very good question. Okay. So, in reality, by the way, so this is what we define as a quantitative error. Okay, so from now on, we're gonna define the difference between the input and the output. Okay, so this output is this output. Okay, so we assume there's a perfect DAC at the output. We reconstruct, based on your ADC code, and we look at the delta between the actual analog input to that V out. That's our quantization error. All right. So in real life, what is our quantization error? You see, look at this, right? It's like a sawtooth. So where are we? Are we here? Are we here? Or maybe we're lucky we're here, which is 0.
Like it's a random dot, like random points.
Kind of random position, right? I think she's right? Does everybody agree? In fact, if you use this ADC to quantize some DC signal, let's say your input is V in DC, and if you are so lucky, your input is right here, right? Just by quantization, you actually have no error at all. If you are so lucky, okay? If you are so lucky, look at all this range, right? There are only a few points where you can get a 0 error, right? So you need to be super, super lucky, to get to that point, right? So usually when we design the ADC, we don't count on that, right? We don't count on the mercy of your input value that you are trying to quantize. That, oh, today is my lucky day. I'm pretty sure, even though ADC I designed has some defect, but I hope that input will be right on this node, right? So we don't count on that, right? All right, so that's really the question is that, what is my V in, right? So because your V in can be like this, right? V in can be a signal anywhere. So you'll be exercising, all this error at different points, right? Depends on your signal statistics. Okay, so how do we analyze this error, right? Because, in the end of the day, we still want to put down some math to analyze ADC just like a mathematician or half mathematician, okay? Because we don't prove a theory or lemma, anything like that, like half mathematician. So how do we do this? All right, so like any engineers, we need to make some assumption. First, we assume the quantization errors is uniformly distributed between minus delta over 2 and plus delta over 2. Okay, does that make sense? So let's look at this. If you say that your input, So this is the minimum value, this is the maximum value, right? It could be arbitrarily coming in anywhere in between. Is my assumption kind of correct that you look at the errors, right? It's like you randomly, sample all these error signals. So you'll be roughly uniformly distributed between plus minus delta over 2. Do you kind of see that? Kind of? Okay. Of course, this really depends on your input signal characteristic, right? So, but most of the time, this is a good assumption. Okay. Especially if you know your analog signal is larger than, or usually is much larger than one quantization step. So one quantization step is delta. Okay, your input has to be much greater than 1 delta. Why? If my input is all within 1 delta, right? So it depends on where you are. If you are uniformly distributed within 1 delta, you probably can still sample all this, it's okay. But just imagine if the input is just a fraction of this delta, you are not uniformly distributed between delta over 2 and minus delta over 2, right? You guys see that? You don't, right? Because you're gonna, center around where your input range would be. Okay. So usually, if your input is indeed larger, right, than the delta, because the input will come in like a sine wave or sometimes, somewhat random input signals, you would exercise all the patterns, right? All these errors within the range. So you're gonna start to sample all this, and that's how you can get roughly uniformly sampled. All right. So that's one condition. The second condition is that typically the higher resolution ADC. So higher resolution ADC means more bits, which means that you have more quantization level. So this staircase, you have more staircase. Okay. When you have more staircase, that pretty much suggests that your input maybe exercise multiple of this delta. Basically, that's the same thing, right? So this is true. So for the higher resolution ADC, generally this assumption of the uniformly distribution between delta plus minus delta over 2, this is very good assumption. However, in the futures, if you design your ADC to a lower end, like a 2-bit, like a 1-bit, what is 1-bit ADC? 1-bit. How do I draw the transfer function? If I do a 1-bit ADC, do I have a staircase? Like this. This is also called comparator. You just compare a value, okay, is it 1 or 0? So in the futures, you see a comparator, you can call that as a 1-bit ADC, that's okay. Yeah. I do see people that, oh yeah, I finally know how to design an ADC, because they know how to do 1-bit ADC. One comparator is 1-bit ADC. Okay. So if you are a 1-bit ADC, this uniformly distributed distribution between plus minus delta over 2, this will be a lot less accurate. Why? Right? Because you see all your sawtooth, right? Now can be like this, right? So you just don't have the luxury of kind of randomly sample this, right? In fact, you're gonna see just in fact, it's not even 2, right? Oh yeah, it's 2. Yeah, it's 1. Yeah. So you'll be maybe just seeing this portion, right? So you're not even randomly distributed over a wide range, right? So yeah, so 1-bit, it certainly is not meeting that criteria. Okay. So here's one extreme example, right? So if your input is a DC signals, your quantity noise is a fixed number. Forget about this uniform distribution or whatever distribution. There's no distribution at all. right? If you input the DC signal, your quantization noise is actually just a constant number. Okay, so that tells you how important that, you know, when we do the following analysis, all this will hold. Okay, all this will hold. Most of the case in real life, that's indeed the case. Okay, you are dealing, you know, what's the chance that your input is always a DC? Very few, right? The closest thing I can think of is like temperature sensor. Like temperature is a value, but it's not true. Right? You see now it's very hot, and to the 90s it's go down. You know, it's still like still very. Okay. Now that we understand how we define our quantization error as a uniformly distributed random variables, so next we're gonna compute the power. Okay, so now we're gonna define this quantization error as a V error, right? And we treat that as a random variable. Now I hope that you guys still have some memory of when you take probability class. How do we analyze the power of a random variable? Okay, so if you forgot, that's okay. Let's try to walk over. So the power of the random variable is basically the second moment, the power of the second moment, right? So what you do is that because this is a random variable, so you do need the probability, right? So probability of x times x squared, right? And you integrate, right? You look at the x squared, so that's your second moment, right? You look at the second moment. You got to look at the probability. You need to average out all the different value, right? Because you see, when x value is very high, of course your x squared is terrible, right? If you have a large x squared can be really large. But if you say that, oh, the probability when x is very high, the probability is actually close to 0, then you have no effect. You agree? Right? Because you know you just don't have that kind of opportunity to being high. Okay. So, what is the probability density function of my V error? Right? Also known as PDF, right? Remember PDF? Not the Acrobat PDF, but the probability PDF. So it's a horizontal line because it's a uniform distribution between where? You see? This has to be uniform between negative delta over 2 to plus delta over 2, right? So this is the PDF function of this. All right, so now help me out. So how should I write this? So x is this, right? So this is x, right?
Negative delta over 2. Delta over 2.
So first of all, you know, we do have a upper bound and lower bound, right? Because we know the maximum and minimum are plus minus delta over 2. All right, what's next? So what's my PB of x?
It will be 1 over delta.
1 over delta.
X squared.
And x squared dx. Am I right? Yeah, I think that's correct. Okay, all right, so let's continue. So I get 1 over delta times, okay, so integral of x squared.
X cubed over 3.
That's cube over 3 from
Delta over 2 minus delta.
delta over 2 to minus delta over 2. So what is this?
Delta squared.
So delta cube, so there's a 1/3, right? So there's a delta cube,
3 times delta cube over.
and then what is 1 over 8? 1 over 8, so 1 over 4,
4 is.
right? Because minus negative 1 over 4, right? So,
Yeah.
sorry, 1 over 8 minus negative 1 over 8.
Yes.
So 1 over 4, so this is 1 over 4. All right? Okay, so what is this?
Delta squared over 12.
Delta squared over 12. This, very important. Okay, in fact, I suggest you to memorize this equation. So next time, if you use a delta squared over 2, it sounds very cool. It sounds like you are a hardcore circuit designer. mixed signal data converter. Oh yeah, I know. Yes. What's your connect step? What's your 1 delta? Oh yeah, delta square over 2. Yeah, that's your noise power. Okay, so. All right, so this is a PDF function, and just to remind you, right, the PDF function, the integral of this probability function has to be equal to 1, right? When you sum up all the PDF area, has to be equal to 1. It has to be 100% probability. Okay. I forgot to mention this delta in the ADC world. Sometimes we also call this as 1 LSB. Okay. So one least significant bit of that step. So 1 LSB is 1 delta. Okay. So 1 delta. And in fact, if you look at the full range here, what's the relationship between the full range and the delta? Full range, right? So full range means that the minimum V in to maximum V in. So that's the full range. Or full swing. Sometimes people call full swing. Sometimes people call that as a full range. So you have full range. What's that relationship between the full range and the 1 delta?
Full range by the number of steps is equal.
By the number of steps. Very good. How many steps do I have if I have an n-bit ADC? So let's say I have a 6-bit ADC. How many steps do I have?
2 to the 6.
Like this is 1 bit, right? 1 bit, how many steps do I have? 2? 2 steps. So if I have an n bit, how many steps do I have?
2 to the n.
Okay. All right. So the delta is the full range divided by 2 to the power of n, and that n being your ADC number of bits. So if you have a 10-bit ADC, how many steps do I have? 1024. That's just a good number to remember. 2 to the power of 10 is the 1024. All right. Very good. So now we derive this quantization noise power. And just kind of like what we did in 536A, right? Remember I said that a lot of times we care about signal to noise ratio. Remember that SNR? In this ADC world, this quantization noise is how we define. Okay, so actually, let me first ask you: is this quantization noise a physical noise? For example, in 536A, we learn about what thermal noise. We learn about flicker noise or shot noise. It's physics. There's a physical noise. It's the Brown motion, right? So you go this fluctuation. Is this a physical noise? No. This is what we call artificial noise. Because you quantize. That's why you have this so-called quantization noise, right? So typically, when we talk about the SNR in this regard, we don't really call that as SNR. It is some kind of SNR, but usually we call that SQNR. Guess what is that Q means? Quantization. Okay, because this is artificial. So SQNR means signal to quantization noise ratio. Okay, so keep that in mind. Why is this number very, very important? This number is very important because it helps us to understand if you do a 6-bit ADC versus a 10-bit ADC, what's the ideal SQNR or the ideal SNR upper bound that you can get, right? Because this is just on the quantization noise. So if you look at the final signal to noise ratio, that number will be greater than this or smaller than this or equal to this. You wanna guess? The actual SNR, I build an ADC, I look at the signal to noise ratio, just like what you learned from 536A. You still can do that. You can look at what's your physical noise, right? Everything. That SNR number compared to SQNR, who is higher?
SQNR will be the
This
ideal.
will be the higher, right? Because it's artificial and I have not even considered thermal noise, flicker noise, right? So that's why this number gives us a very good guidance. So you know you cannot exceed. No. All right. So let's try to compute this. So first of all, the LSB, I think I just talked about this, right? So 1 delta is the full scale divided by 2 to the power of n, right? We just talked about this. So this is 1 delta. Okay, so within this full scale range, right here, how do I compute the so-called signal power? In 536A, how do we compute the signal power?
Integrated
Integrated
over the period.
over the period.
What kind of signal?
Sinusoidal.
Sine wave, very good. I've been waiting for that magic word, sine wave. Actually, I think I might have mentioned in 568, right? A lot of times the circuit that we build, we just like to treat as if the input is a sine wave. And just in this case, it will be a full scale sine wave. Okay, so we're gonna treat that, the input power will be as if the input is a sine wave. Okay, if this is a sine wave, what is the power? So again, this is in dB. This is in dB. So this will be 10 log signal power divided by the error power, right? So 10 log. Okay, sine wave power is the amplitude squared
Divided by 2.
divided by 2, right? Amplitude, so what is amplitude? What's the amplitude of this sine wave? I know my drawing is not very good, but imagine half of that, right? So VFS over 2, what did you say? Square divided by 2, right? That's the signal power. Okay, next I need to know what's the quantization noise power. So what is that magic equation? Delta square over 12. Okay, so what is my delta? VFS divided by 2 to the power of n, right? So that's delta square over 12. Very good. Okay, so I think we are done because why? VFS, they cancel out, right? Turns out that the exact VFS number, the full scale, I don't care you are 1 volt, I don't care you are 10 volt, I don't care you are 1 millivolt. You know what? It doesn't matter. It's all comes down to the same thing. So I get 10 log 3 half times 2 to the power of n. All right. So if you expand this, you get 6.02 times n plus 1.76 dB. And this will be the second equation that I suggest you to memorize this. Your SQNR, given the n-bit ADC, it will be about 6 times. 6n plus 1.76, and if you think that is beyond your memory bandwidth, you can just remember as a 2. So 6n plus 2. Sometimes people also do that, right? If you don't want to waste too much of your memory bandwidth, just 6n plus 2. That's also okay. If your memory is okay, 6.02 n plus 1.7. They are close. The reason I suggest you to memorize this because all the engineer I found, they all use this as a guideline. Okay, so there will sometimes they will say, okay, yeah, I built this analog system. Okay, it's about 5 bit. And then you're saying, okay, what are you talking about? You don't even build the ADC. You just said that, okay, this is about 5 bit system. What do they even mean? So what that means is that it's equivalent to 6 times 5 plus 1.76. That's the SNR of that system they are building. They will just say, oh yeah, this is equivalent to 5-bit system. As if you cannot design a 5-bit ADC to quantize that SNR they actually design. Okay. So because of that, this become a super important numbers. And also another good reason is that most of our analog system has ADC. That's a fact. Very rarely that you will find a system that does not have ADC. Very rare. Very special case. Okay. 99% of the electronic circuits in the world, they always have ADC. That's why this class is so important. No matter what application you're gonna build in the future, there gotta be ADC. Or DAC. When I say ADC means that there's also DAC, right? So there's always this conversion between analog and digital world. So this, you always have a market. Okay, so you got to design something there. Okay, so this 6n plus 1.76 dB will be hand in hand to describe this SNR and the resolution, basically, of your system. Okay, like ADC. All right. So if I add 1 bit to your ADC, what's my SQNR or SNR, right? So SQNR improve 60. Okay. So then some of the engineer, when they say, oh yeah, I improved the SNR, so let's say 3 dB. You know what they tell you? They say, oh, I just improved half a bit. So in the future, if you hear somebody tell you, oh, I just do this, I improved by half a bit, then you know that's what they meant. They just improved the SNR by 3 dB. So that's kind of the jargon that people say, in our field. Okay, so and one more thing here, of course, I assume it's a sine wave input. In real life, what's the probability that you actually have a purely sine wave input? None. Nothing, right? Because the pure sine wave has no information. So no nothing. Okay, in the physical world, that would be sine wave. All right. So then they say, okay, why am I using sine wave? I guess when we do the calculation, it's just easier. That's just a fact. The sine wave, right? Okay. So, and also, even if in the future you have a different input waveform, it turns out that the difference is not that big. Okay. So you say, okay, instead of sine wave, it's some kind of modulate signal. Okay, it's a QAM signal, OFDM signal. All right. So ultra high-band signal. Who cares? Whatever that signal that you do, you can compute this SQNR. Turns out that it's not far off from this. It's actually pretty close, right? So usually in industry, when they design the actual system, what they would do is that they would first model. So when they compute how many bits they actually need for their system. So first of all, they would apply this equation to get some rule of thumb quickly. But when they get to the point where they actually need to define, okay, do I need a 7-bit? Do I need an 8-bit? What they usually do, they will actually model this quantization steps, right? So the behavior model, basically ADC. In fact, I think your homework I will ask you to do this. Okay, so you will have some behavior model of the ADC, and you send in the actual signal, and you look at what's SNR at the output, right? So that's exactly what people do in real life. Okay, but nevertheless, having this sinusoidal input help a lot. Okay, give you a lot of intuition. You will anchor it to your design point fairly quickly. And by the way, one last thing I want to point out: even though the SQNR may be slightly different, but that 6 dB per bit will not change.
How would it be possible to get like a 3 dB improvement in SQNR? How can you just add half a bit?
How do you add half a bit? You can do half a bit. If you talk about the ADC, right? So even though it's a 2 to the power of n quantization levels, But when you actually design it, who said that you have to only follow this power of 2? Right? So for example, 9-bit ADC, how many level? 9-bit ADC, how many level do I need? 5, 12. 10-bit ADC is 10, 24. So your gap is 5, 12. It doesn't mean that, hey, I cannot do somewhere in between. Who said that you cannot design 600 steps? Who said you cannot do 700 steps, right? So that will be somewhere in between. So then you design ADC is 9.5 bits or 9.6 bits ADC. You are right, the actual output will probably has a 10-bit wide. But if you compute the actual SQNR, you will only get 9.5 bit or 9.6 bit. So it really depends on that conversation level, right? I think that's, thanks for bringing this up. So this is very important, right? Even though I say that the conversation level is 2 to the power of n, it doesn't mean that, you know, in real life you cannot specifically always design for 2 to the power of n steps. Nobody say that. Okay, it is true most of the time. That's what we do. But I've seen a lot of specialized electronic systems. They do somewhere in between. How do they decide that? That's what I just told you. They actually build a behavior model. They study. Oh, instead of 1024, I think 745 steps looks to be optimal for my system. Okay, then they do it. They do it that way. Okay, that's a good question. Any other question? Yes.
So here it looks like it really doesn't depend on the full scale, whatever your full scale voltage is, right? Because you're just getting cancelled.
Yes.
But before you said that the quantization step, if your full scale voltage is comparable to the quantization step, then you can't really generalize your quantization error as a.
Yeah, if your input is so small, yes. So imagine if this
it
is
depends,
smaller.
the SQNR still depends ultimately on the full scale voltage.
Yes, it is. So actually that's actually a very good question. So let's say this is my full scale. Okay, let's say this is 1 volt. Okay, this is 1 volt, and I knew because you designed this ADC is 1 volt swing input. Supposedly I can inject a 1 volt swing input to you, but for whatever reason I say don't bother. He designed for 1 volt full swing. I'm just gonna give him half of the swing. So I'm gonna give him this. Half. What is my SQNR? So my amplitude scaled down by half. Become half. How many dB difference? This is amplitude. Amplitude become half in dB. 6 dB. 6 dB difference. Okay. So that's basically what you are sacrificing. So you design an ADC with this 1 volt swing. If you decide that, okay, let's don't forget, SQNR, try to specify what's the upper bound, right? What's the maximum SQNR you can get. In order to get the maximum possible SQNR, of course, when you inject the input, you have to inject the full swing scale so that you can max out your input signal power. Does that make sense? But it doesn't mean that you always need to do that, right? At times, your input can become smaller. Of course, it's possible, right? Even the human speech, right? Sometimes I can just voice out, sometimes I can just whisper. I can whisper, right? So then my signal swing becomes smaller. So if I whisper, the signal is smaller, then your SNR, right, or SQNR at that point, it will go down, for sure, right? It will go down for sure. Yeah, but like I said, you know, when we define the SQNR, typically our common consensus is that we are exploring what's the maximum achievable SQNR. So it is still correct that you just assume that's a sine wave with a full swing, right? But just keep that in mind. In the future, if you're gonna use this ADC that you designed for a particular system, and whoever designed the previous block and say that, oh no, I'm sorry, I'm just gonna give you half of the full swing, then you have to make him understand or her understand, fine, if you're gonna do this, you're gonna waste. You waste, how many bits do I waste? You said 60 bit, right? So you lose 1 bit. So basically, whatever effort that you design your ADC, you design 1 bit more. That's basically what that means, right? Because you don't need to accommodate this one, but you could have just designed ADC like this. You can throw away 1 bit and just have that. Okay, so that's a very good question. Remember in the first lecture I showed you in a wireless system, right? So usually they have the amplifier, right? And then they have something and they have ADC. So now you know why. Why do I need an ADC? Sorry, why do I need an amplifier before the ADC? Thank you, because I want this to expand as close to the full swing as possible. Otherwise, why do you, as your colleague or you yourself designing the ADC with all the sweat that you're doing, okay, you finally get this to work, and then in the end, nothing, right? Your input is nothing, so small. You waste all your effort. Yeah. So that for that reason, that's why oftentimes you do need an amplifier. That's why we have 5368. That's why we have 5368 for that reason. You need an amplifier. you need a gain. So now this is where you combine 5368 and 631. I still stay with what I told you before. If one day one of you or a couple of you figure out a super duper ADC, you probably don't need an amplifier. Why? You see, your N become very large, right? So even though yes, when you reduce this, you're gonna lose 6 dB or whatever, but because your noise floor is so small to begin with, you still can receive the signal. You don't need an amplifier, right? So this is what I said earlier. In the first lectures, that if one day you guys figure out how to design this amazing ADC, there's pretty much no role for pre-processing block like amplifier. This pre-processing block. And also remember we talk about aliasing, right? How do we take care of the aliasing? The filter, right? So yeah, so if you can get ADC super duper, like sample super fast, high speed, you can also get rid of relax the filter a lot. Yeah, so yeah, so I feel that the whole world that we are learning pre this class, anything that you learn, it's just because we don't have a good ADC. So we need something else to help the ADC guy. Yeah, the ADC is like, they need to work harder, right? That means that you guys need to work harder, right? In fact, we have one government program right now. They say, oh, your ADC is consume too much power. So can you guys build one circuit topology that get rid of the ADC? And that's what we're working on right now. So ADC guys need to step up and help the world, right? All right, any other question? If not, let's take a short break.
他现在给我的是 off grid， 就是代表它有个0.25区，我是0.25是来的。
所以我后来滑到第就是现在一直冲，
就是它的每个单位格是0.00， 但它现在我连着这两个中间的单这距离是0.002，所以就它没有办法，这个 reset 需要这么高，然后它就会用 ERC error。但我不知道凭什么，它凭什么？我现在。